Welcome to this talk about principles for building operators. My name is Julian Fischer. I'm CEO of a company called NA. We build application developer platforms and are enthusiasts for data service automation. In particular, we've automated a bunch of data services in the past several years. Among them services such as Postgres, which will be my favorite example today. So entering the world of Kubernetes, we also started to write operators. And in this talk, I'd like to share some of our experience. The talk will cover several aspects. Among that will be general statements about data service automation and concepts, covering also methodology with general challenges, as well as principles and strategies how to deal with data service automation. We also will talk about Kubernetes and particular technological challenges that will come up with writing operators, and also propose some solutions how to deal with it. At the end, a summary will be presented, and we'll have some time for questions and answers. All right. Data service automation in general, you can interpret it as in various different ways. So in order to focus and narrow the scope a bit, we are talking here about fully automating the entire lifecycle of a wide range of data services to run on cloud-native platforms across infrastructures at scale. We're going into details of that a bit. So the scope of the operators we want to write is not about a single Kubernetes cluster that runs somewhere and needs to operate a single Postgres database, for example. No, there are many various steps in between, but the case we really want to get to is a scenario where there are lots of Kubernetes clusters with lots of different operators and many service instances. So basically, many operators and many service instances. In particular, the size could be hundreds to thousands of data service instances. We have environments where there are more than 1,000 different data service instances being automated based on our automation. And these accounts usually tend to grow and not shrink. So it's basically setting a high standard for automation to allow these environments to be operated efficiently, especially because scale matters. It's a very different thing to let's say operate a dozen databases compared to 1,000. And each data service instance matters, even if those organizations are large and their data is distributed across many different databases. Each database has an owner, and these owners, they'll care. I mean, of course, there are databases which are less important. There's this test database that has been created once, but since then has been forgotten and nobody really cares. But most of the databases, they do have production purposes, and there are stakeholders, depending on the availability of those data service instances. So this basically generates high barrier of entry for automation to work, properly in those organizations where a lot of databases are required, because they're usually grown organizations with policies and requirements for data service maintenance. They have DBAs, they have sysops, and they have their operational standards. And automation needs to live up to this standard. And therefore, we'll look in this talk a bit deeper into how to do that with Kubernetes, and always come back to what customers will want and how to combine and how to make it possible. So, what are ways to implement an operator? Before we go into details, let's have a bit of a summary. Well, the first and maybe most fundamental way to implement data service automation would be to use a Kubernetes CRD and a corresponding controller. So let's say a Postgres CRD and a Postgres controller. Well, this is basically what you also would be doing using the operator SDK. However, you'd have additional guidance on how to describe CRDs and how to also write your controller. So we'll assume in the remainder of the talk to use the operator SDK. There's also another option which I have covered in a separate talk, data service automation prototyping with Kudo. It's a generic operator. It allows you to declare an operator instead of writing a lot of code. It's basically a workflow machinery to apply Kubernetes YAML specs. It's pretty interesting if you want to get something done quickly, and therefore is worth noticing. Maybe you want to look up that talk if that's of more interest to you. All right, so developing an operator is an endeavor that has a certain complexity, and therefore let's think about what are the things we'll have to do in order to get it done. If you approach a data service for the first time, let's say Postgres or RabbitMQ or Kafka or anything, the first thing you have to do is understand what is the data service for, what is the primary use case you intend the data service to be in. Let's say interview your target audience if you're an organization with many application developers and you aren't an application developer. You have to talk to these people and ask them what are their expectations about data services. Let's take Postgres as the example, my favorite example. Application developers could state that they want to have asynchronous replication with Postgres, and before automating that, we need to understand how does asynchronous streaming replication in Postgres work, how to create a streaming user, a replication user, how to monitor replication, for example, observe a replication lag or detect failures of a primary node, and provide mechanisms to fail over to a new leader by electing a leader using a quorum strategy. So all these things are covered already with documentation and tutorials. So basically the operational model level 1 covers what a sysop or DBA would do. You'd collect this information and compile it into, let's say a tutorial style collection of things you want the automation to do. In the next level, you'd have to think about how to turn this into a container image. Maybe there is a container image for Postgres. Maybe you have to add container images to add your cluster manager, for example, Rep Manager or Patroni or anything alike. And once you've done that, you can provide YAML specifications to create a service and a stateful set utilizing the container images and building your first service instance manually or semi-manually using kubectl. So in this stage, you'd be between modifying the container images and adjusting your YAML specifications a lot, maybe revisiting default configuration values you want to set and so on. The next level is the operator itself, which means you'd have to use the operator SDK, for example, if that's your choice. Describe CRDs, how to represent a Postgres object in Kubernetes API terms, so to say, by providing a Postgres structure and teaching the Kubernetes API how to do that, as well as writing a controller that actually translate that specification into something more meaningful, such as a service and a stateful set to represent your data service instance. But that's not all. Level 4 is also important. If you think about the idea of distributing this operator to many Kubernetes clusters, you also need to manage the lifecycle of the operator itself. You need to be able to distribute it into many environments and to update it as well. And that's the level 4, Whether you do that with Helm or whether you do that with the Operator Lifecycle Manager or anything else, doesn't matter, as long as there's also automation for that. So if you haven't done much with Kubernetes operators, here's a brief summary. The first concept you should be aware of is that of custom resource definitions. So the Kubernetes cluster API is extensible, and it's based on the Open API standards, and you can provide a so-called custom resource definition, teaching the Kubernetes API a new data structure. So in this case, for example, we have a custom resource definition with the name of PGS, and this PG object is providing two different properties, replicas, numeric value, as well as Postgres version here with a default of 12.2. So simple and straightforward. You can, create objects that will be of the kind PostgreSQL. Short names will be PG and PGs. And that's basically the CRD. You once applied to the cluster, objects will look like this. You can then create objects by using kubectl and create these objects. Kubernetes will provide an endpoint for you, receiving the object specification and storing it as a desired state to have such an object in its etcd. But it doesn't know how to build a Postgres instance, of course, which is the responsibility of a controller. So the controller will take the desired state provided as this specification, for example here, a Postgres instance with version 12.2 and 3 replicas. And the controller will then have to provide some logic that will read that specification and translate that into secondary resources. So in this case, a service and a stateful set. So we have two sets of resources, the primary resource, which would be the Postgres object, as well as the secondary resources, which will comprise a service and a stateful set. Now the controller will monitor both. It will monitor the primary resources for changes, for example, changing the number of replicas or changing the Postgres version, and then have to translate it into changes of the secondary resources. For example, by modifying the number of replicas in the stateful set, or by referring to a different container image and thus restart the stateful set with a different Postgres version. Also to be said, if a secondary resources changes, for example, you delete the stateful set, then the controller will be notified as well, and it has the opportunity to recreate a stateful set to reconcile into the desired state again, where there is a service and a stateful set. This is pretty similar to other hierarchically organized resources in Kubernetes, such as deployments, replica sets, and pods, where if you have a replica set and delete a pod manually, the replica set controller will recognize that and recreate the pod. This is pretty similar here. You can create a controller that behaves similarly. So in the first approximation, you can imagine a controller as something that takes a primary resource and generates secondary resources from that. In the most simple case, both of these resources are Kubernetes resources. Whether it's a service or it's a custom resource, such as, for example, a Postgres, in this case, service and stateful set, they are both Kubernetes native resources. We will later see that a controller does not have to necessarily translate into Kubernetes native resources as secondary resources. The service binding example will show that you can also reconcile external resources. So, for example, a Postgres user in a Postgres instance you've created earlier. So controllers, basically, they receive events about the desired changes of the desired state and reconcile them into secondary resources, which could be internal to Kubernetes or external.